to talk about Tech4Diet RGBD-based framework to acquire, visualize, and measure the human body for dietetic treatment. I hand it over to you, Andres.
Okay, I'm going to start my presentation. Okay, let's go. Okay, thank you very much. Thank you very much, Ethan, and all your group for your kind invitation to this Zero Tech talk. And thank you, all of you, for coming. Okay, my name, I'm going to make my presentation also. I am Andres Fuster-Guillot. I am the head of a research group. This is the Applied Intelligent Architecture Research Group. This is a group inside the Department of Computer Science and Technology. And this department is a part of the University of Alicante. You know, Alicante is a city in the southeast of Spain. And we are in the department over there. Okay, I think that you're currently watching my presentation. We are going to talk today about a research project. The acronym of the project is Tech4Diet. And we are going to talk about to provide our LGBT-based framework to acquire, visualize, and measure the human body for dietetic treatments. The outline of the presentation is organized, as you can see in the slide. First, we are going to talk about some context of the project with the objectives of the project. Then we are going to talk about some methods of the pipeline of the process of 3D body reconstruction, that is the acquisition of the 3D models. In the third part, we will talk about some methods to analyze deformation, methods for 4D, that is 3D plus time visualization of the deformations. In the fourth part, we will talk about the adherence, that is the evaluation of the effectiveness of the use of these technologies over the adherence to nutritional treatments. And finally, we will summarize some contributions and the objectives of the following project, our new project that we are going to begin in the near future. Okay, let's go with the context of the project. Please only let me make a short mention about the funding organization. That is the Spanish Agency for Science, Innovation and University. This project has been running from 2018 up to date. The head of the project is my colleague. He is here with us today. Is Jorge Aferin Lopez, and I am Andres Fuster, the coordinator of the research group, Applied Intelligent Architectures. And our main motivation in this project is to try to decrease the high impact of chronic diseases caused by obesity and on healthcare cost. We know that many current treatments focus on short term, and our motivation is to try to contribute to improve adherence to treatments by using different kinds of technology related to 3D. Our hypothesis is that providing realistic 4D visualizations may increase the treatment effectiveness and maintains long-term adherence to nutritional treatments. This is our hypothesis. Then, to get this goal, we have organized three main objectives. The first objective is acquisition, that is the acquisition of the 3D models of the human body. The second big objective is the generation of 4D models. When I say 4D models, I'm talking about 3D plus time to analyze the deformation of the bodies. And the third objective is adherence, that is the evaluation of the effectiveness of the visualizations of the models over the adherence to nutritional treatments. Okay, let's go a little more deeper in each of these objectives. First objective is acquisition. We want to develop an accurate and flexible method for the 3D acquisition of the human body, taking in account shape, color, and fat distribution. And to achieve this objective, we have organized 3 main tasks. The first one is the 3D acquisition of point clouds of human body using low-cost RGBD cameras. The second task is obtaining the 3D geometric body models using meshes. And the third task is obtaining the texture representation of the body to get realistic representations of the people. Okay, the second objective is deformation. That is the development of a 4D model for the analysis of visual appearance change of the human body. To get this objective, we have organized 4 principal tasks. The first task is to provide visualization system using virtual reality devices. The second task is to provide methods for the anthropometric measurements of the body. The third task is related to provide different methods to face the problem of deformable registration. And the fourth and last task related to objective 2 is to provide a 4D model that is a model of with 3D plus time to analyze the morphological change of the appearance of the people that is carrying a nutritional dietetic treatment. The third objective is related to the evaluation of the effectiveness of the visualization of appearance change over adherence. And we are developing nowadays different tasks. The first one, we are developing a dietetic and nutritional intervention with a specialist. We are going to evaluate the adherence. The adherence, this is the motivation of the patients that are taking this nutritional intervention as a consequence of using the technology. And we are also working in a third task, developing an anthropometric study with different types of measurements in monodimensional measurements, 3-dimensional measurements, and 4-dimensional measurements, taking in account the change in time. Okay, to do so, we are working in a multidisciplinary research group. I'm going to summarize the main components of the research group that are developing this project. The coordinators of the project we are the coordinators of the project, the Computer Science and Technology Department from the University of Alicante. Jorge is the principal researcher. And we are working with a health psychology department from the University of Alicante in charge of the analysis of the health psychology part of the project. And we are working with a nursing department for the part of the intervention with dietetic treatment. But we are also working with international groups. We are working with universities Jean Monnet in Saint-Étienne, with Professor Marc Sevan and Amaury Havard. And we are also working with University of Edinburgh with Professor Robert B. Fisher. Okay, let's go a little more deeper with the first objective, that is the acquisition and the 3D reconstruction of the human body. Okay, to meet the requirements of the project related to accuracy and realism of the representations, at the beginning of the project, we decided to use a network of RGBD cameras, place it around the body, and with the body static in the same position. Because our previous experience using RGBD cameras and the model, only a single RGBD camera and the model rotating in front of this single RGBD camera didn't meet the quality requirements due to the movement of parts of the body. You can see here our paper, an iterative method for 3D body registration using a single RGBD sensor, where we get good results, but these results were not enough, didn't have enough quality to meet the requirements of the project. Then we decided to use a network of RGB cameras inside a cabin. We have tested different structure dimensions, number of cameras, position of cameras, different configurations. Nowadays, we are working in a cabin with 12 cameras, but we have tests from 8 to 13 cameras. These cameras are allocated on a 4 aluminum mast. You can see here the structure measures nowadays. And we have compared different RGBD sensors from the market, and we have decided to use the Intel RealSense D435. This is an active stereo infrared camera that provides the appropriate characteristics related to field of view, depth accuracy that meets the requirements of the project. And we are working with these cameras and this cabin that you can see in the right image today. Here you can see on the right image, you can see an example of a green cube, the different views of this green cube from the different cameras allocated in the cabin. And in the left image, you can see the typical two images provided by our RGBD sensor. You can see in the left, the RGB image, and in the right, the depth image. And inside the image, you can see the green cube. We are using this green cube as a basis from the calibration process that I'm going to explain a little later. Okay. In order to address this reconstruction of the human body, we have used the following pipeline. First, we take the acquisition of very noisy point clouds. Okay. Then we go to the second step, that is pre-processing the point clouds to try to reduce noise. The central step is registration to try to unify the different point clouds provided by the different cameras. The fourth step is the mesh generation, And finally, we get the texture projection of the images over the mesh to get these realistic representations. But before starting this process, we need to perform a preliminary configuration step. This is the calibration of the system. We only do this step one time. If we don't move the cameras, we don't need to do it all the time. We face two types of calibration. Intrinsic calibration to correct the distortion of images caused by lens, and extrinsic calibration to try to unify the different views of the different cameras allocated on the cabin. Okay, let's go with intrinsic calibration. In our paper, a quantitative comparison of calibration methods for RGBD sensors using different technologies, we have studied several classical methods to face intrinsic calibration like Barros, Boget, or Herrera. But nowadays we are using a combination of methods. First, we are using the Intel RealSense SDK included in the camera tools. And this SDK involves the intrinsic calibration of the RGB sensor. You can see in the image in the right part of the camera, the RGB camera, the RGB sensor. We have to calibrate, the SDK calibrates this sensor, but the intrinsic calibration related to the infrared sensors provided by the camera. But we also, in the SDK, we also face the extrinsic calibration, that is the alignment of the two images provided by the camera, the color image and the depth image. You have to properly align these two images to get good results. But at the end, we also incorporate some ad hoc tuning by using 3D markers, as you can see in the image, to try to definitively improve the quality of each of the cameras inside the cabin. Okay, regarding extrinsic calibration, our main contribution in this field is an accurate and fast calibration method. In the first paper, iterative multilinear optimization for planar model fitting under geometric constraint, we have developed a fast method for the reconstruction of plane-based models with high accuracy. In particular, we have reconstructed the cube with high precision. And in the second paper, we are working in this paper nowadays. We are using this the reconstructed cubes as 3D markers for high accuracy calibration of the RGBD cameras of the network. And this is the method that we are using today in the system to provide accurate representations. Here you can see the acquisition of the cube, that is the 3D marker, in different positions from different cameras. And with these images, we reconstruct the 3D model of the cube. And we use this 3D model for the calculation of the precise, accurate relative positions of the cameras inside the cabin. We get the transformation matrix. This is a key point to get good results. Coming back to the pipeline, the first step is acquisition. The first problem of acquisition is to synchronize the cameras to get the images at the same time. We have used a semaphore management strategy to address this problem, and we have used the Intel's SDK provided by RealSense as the basis for the development of the software. You can see here in the video the cabin that we are using in the video. But the point clouds that we get in the first step are very noisy. Then we need to use some methods to try to improve these noisy point clouds. And nowadays we are using 3 main filters: a median filter to try to reduce noise in an efficient way with a single pass method, a bilateral filter to smooth edges and areas, and a statistical outlier removal filter, SOR, to remove edges, noise, and to remove very important outliers. But we combine these filters with a truncating strategy. The point clouds are truncated in the zeta axis to remove points beyond the center of the captured area. And with this, we get improved point clouds. The central step is rigid registration. The rigid registration aligns the different point clouds in a single 3D coordinate system, applying the transformation matrix obtained from the extrinsic calibration of the first step. As you can see in the image, all the data elements in a rigid registration are transformed equally. This is different from a deformable registration. You can see in the image, in the right image, you can see the different point clouds in different colors provided by the different cameras in a unified coordinate system. We have used different registration strategies using a single reference camera, that is one camera as reference, and transform the rest of the point clouds to obtain a unified data set, and a multi-row reference camera with a reference camera for each row. In the video, you can see the registration of the different point clouds that we do automatically, applying the matrix that we obtain during the calibration process. But once we have the unified point cloud, we still have some problems with the point clouds. We have some missing point in some folded areas, like armpits or crotch. And the solution for this is to use body templates, that is meshes, to adapt the templates to the point cloud with a deformable registration, the CPD. I will come back these algorithms later, to fill in the areas with missing points. In the image, you can see the point cloud with the missing points. in the central image, you can see the template, and in the right image, you can see the point cloud completed. Then, with these steps, we get the complete point cloud, and we need to face mesh generation. Okay, for mesh generation, we have compared different methods like ready projection or matching cubes, but the best results we get was with the Poisson surfacing algorithm to reconstruct a triangle mesh from a set of oriented 3D points by solving Poisson systems. We have adjusted some parameters for the triangularization level, like depth parameters, that makes different size and number of triangles of the mesh. Here you can see the point cloud and the mesh that we obtain using this Poisson algorithm. And finally, the last step is texture projection. Inspired by the method from Calieri for raster projection and texture generation, we have developed our own method that takes as input the mesh model with the normals for each triangle and the RGB images provided by each camera and the relative positions of the different images of the different cameras. And with this input, we apply an algorithm that provides this output, the texture map based on the projection of the different images over the triangles of the mesh. We do the unwrapping of the model, and we calculate the best possible projection for each triangle based on the normals between the triangle and the position of the RGB camera, of the RGB images provided by the cameras. But we still have problems with irregular texture projection between neighboring areas provided by different cameras in different conditions. Then we have to use some optimizations, local optimizations, to estimate small groups and smooth edges, and some global optimizations to try to reduce the color difference between different images provided by different cameras. In the left image, you can see the texture projection with some texture difference. And in the right image, you can see a smooth texture with an improved result. Here, you can see a comparison of texture projection methods after applying optimizations and before and after applying the optimizations with the smooth texture projection. Here you can see another video of the texture projection process. You can see how we project over the triangles the different parts of the images provided by the cameras to get the proper result. Okay. You can see more models and videos in our web page. The web page of the project is tech4Diet.dietetic.ua.s. You can find different models and different videos about the system and about the methods and the information about the project and publications. Here you can see one of the videos that you can find in the web page. In this case, is a dressed model, but we are working also with undressed model because they are taking a dietetic treatment, and we have to measure the dimension of the body. Okay, that's all for the first objective. Let's go with the second objective. This is related to deformation, that is 4D model visualization of the human body. We have, in this second objective, we need to develop a 4D model for the analysis of visual appearance change of the human body. To get this objective, we have organized 4 tasks. First, the development of a visualization system using virtual reality devices. The second is develop some methods for the anthropometric measurements of the different parts of the body. The third task is some methods to face the problem of deformable registration. And finally, the fourth task is to provide the 4D model to try to analyze the morphological change of the bodies during the time. Okay, we have developed a software using Unity that provides different functionalities. For example, you can see here a video. You can scan the patients, you can manage the patient's data, register new patients, view the history of sessions, and of course you can visualize, change the point of view, and navigate through medical information from the different sessions. The system provides comparisons of the body models, overlapping different sessions with different sessions of one patient. Here you can see a video with 2 overlapping models, one with texture and the other one with a transparent red texture. That is very useful to try to compare the loss of weight of the patients. You can select any 2 sessions to be compared. Regarding the virtual reality system, the virtual reality system is synchronized with the computer specialist, allowing the interaction between both systems. Then the patient can see what the specialist is projecting, comparison of sessions or evolution of sessions. But as you can see in this video, the movement of the user's head is transmitted to the rotation of the 3D model, and this lets the patient to change the point of view of the model. Okay, regarding the second task, the anthropometric measurements, we have published a specific paper on the technique for obtaining measurements. The method that we provide works with 2 steps. First, we launch perpendicular rays along the circle, storing the points of collision with the mesh. And once we have the collision points, we calculate the addition of the distance between points to get the perimetral measures. Here we can see how the circle is positioned in the application to obtain the proper measurements. You can adjust the dimension of the circle, the orientation, the rotation, the height, the different parameters of the circle in order to get the proper dimension. But you can also get volumetric 3-dimensional measurements. We use the same method for the volumetric measurements. We integrate different sections of a cylinder to calculate the volume. Here, you can see how the cylinder is positioned to obtain the measurement, the volumetric measurements, adjusting the position, orientation, and allocation to try to get the proper volumetric measurements of the bodies. We have, as a result of this system, we have published a paper that you can see in the image, LGBT-based framework to acquire, visualize, and measure the human body for dietetic treatment. In this paper, we have compared our method with the state-of-the-art methods regarding accuracy. We get a relative error under 1%, improving other methods reviewed in the state-of-the-art. Then Now we are working in the project with these methods, taking measures of the bodies to try to analyze the parameters. Regarding deformable registration, the deformable registration is different from rigid registration. In deformable registration, we need to align the data sets using different transformation. We can find different types of deformable registration: skeleton-based isometric registration, elastic registration, free deformation registration. In our paper, a comparative study of registration methods for LGBT video, we have studied different methods for this rigid and deformable registration. In the case of deformable registration, one of the most popular methods is CPD, based on Gaussian mixer models, developed by Mironenko. In our paper, 3D non-rigid registration using color coherent point drift, we propose a modified version of CPD to incorporate color information. The proposed model improves CPD in situations where the color information can be used. For example, in the image, you can see how a square is deformed over a fish, taking in account the color information and improving the results of CPD in this case where color information can be used. We also have studied the use of deep neural networks to face the registration problem. In our paper, when deep learning meets data alignment, we have reviewed these deep registration networks. That is, deep networks used to face the registration problem. As a consequence of this previous study, we have just published a paper called Local Global Based Deep Registration Neural Network for Rigid Alignment, where we have proposed a network architecture to estimate the translation and rotation to rigid registering 2-point clouds. The network architecture is divided in 2 parts. The first part is a feature selection based on PointNet and PointNet Plus, and the second part estimates the rotation using a FlowNet based network. This is only to face rigid registration. The final task related to second objective is to provide the 4D model. We have designed a 4D model with a graph structure where each node of the graph contains information about the different parts of the body. For example, we are storing in this graph geometric information of the different parts of the body, the partial meshes, texture projection information with the partial texture maps, and the most important, the dynamic change over time, that is the deformable registration of the different parts of the body evolution over time. To do this, the pipeline that we are using is, as you can see in the image, the first step is body part segmentation. We segment the different parts of the body, arms, trunk, legs. Then the second step is aligning the sequence of separated parts of the body for different sessions in time. We do this with rigid registration. Imagine, for example, the leg, a sequence of legs, or a sequence of arms, of a sequence of trunks of a person in different sessions. And the final step is the deformable registration. We register in a deformable way the sequence of the segmented parts of the different bodies in different sessions. In the image, you can see the segmentation, the rigid registration of the parts of the body, and the deformable registration. Here you can see an example of the 4D model. In the left image, you can see a sequence of models with weight loss. You can see a little effect of the weight loss in the model. In the central part, you can see the segmented model. And in the right image, you can see the 4D model. That is the 4D model to fat loss representation. Okay, the lighter the green color, the greater the fat loss. Here in the video, in this model, you can see how the abdominal area and the chest represent the greatest variation in volume due to the fat loss. Okay, this is all regarding the second objective. Let's go with the third objective, that is the adherence, the effectiveness of 4D visualization. Okay, in these objectives, we want to evaluate the effectiveness of the visualization of apparent change. Now we are almost at the end of the dietetic and nutritional intervention. We are working in this dietetic and nutritional intervention with 87 male and female Spanish volunteers with overweight and obesity, organized in a control group and an intervention group. In the intervention group, we are using the 4D visualization of the technology that I have presented. And in the control group, we are working with a traditional dietetic and nutritional intervention to compare. We have been developing individual and group interventions during 7 months from December 2020 to June 2021. We are at the end of this part of the project. And we have organized six individual sessions for each patient. Remember, 87 patients. That is 522 sessions with anthropometric data, medical data, and psychological data. Our colleagues in the psychology and nursing groups have been working in this paper right now. They are analyzing the role of body fat mass and visceral fat in executive food function. And they are analyzing the association between markers of adiposity, like body fat or visceral fat, and domains of executive function, cognitive flexibility, inhibition, or working memory, for example. And they are also analyzing improvements in adherence to nutritional treatment. This paper is under review. Then we are at the end of the collecting of the process of collecting a very important data set with anthropometric, medical, and psychological data. We have information related to anthropometric measurements with the 4D models, these graphs with geometric information, the meshes, the texture, the dynamic change that we get with the deformable registration, the anthropometric measurements with the perimetral and volumetric measures, the chest, the waist, the hip, and their evolution. We have some medical data, weight, visceral fat, blood pressure, cholesterol, and so on. And we have psychological data, executive function, cognitive flexibility, inhibition, monitoring, working memory. We are at the end of this part of the project in the process of collecting this data. And we are currently starting to select the clustering methods to be used and the variables to be correlated. The objective is to study if there are combination of variables able to predict the behavior of other variables. For example, we are going to study the fat accumulation patterns, as you can see in the image, or relations between different combination of anthropometric, medical, and psychological variables. For example, as we have already seen, if the body and visceral fat can have influence of, for example, the working memory. Okay, this is the end of the third objective, and let's go with the conclusions and the contributions. Only I would like to highlight and summarize our contribution related to the objective 1, the acquisition and calibration. We have provided a fast and accurate calibration method and an acquisition system that meets the requirements of the project regarding the accuracy of the measurements and the realism of the representations. Here you can see the 4 papers published related to this objective. Regarding the second objective, the deformation, we have provided a visualization and measurement system and a model to face the problem of deformable registration, and the 4D model to be able to analyze the deformation of the bodies. Here you can see the publications related to this objective. And finally, now we are working in the last part of the project. This is the nutrition and psychological intervention, and we are working in the analysis of the data set, the anthropometric study, and the adherence analysis. We are working now in these publications. Okay, only a short reflection about the future of the project. Now we are applying for a new project that we call Tech4Diet Predictive plus Home. And we are trying to face 3 main objectives in this new project. First, the development of a flexible method for the acquisition of 3D models of the human body. We want to be able to get the models from the home with a more flexible technology. The second objective is the development of methods to obtain predictive models of the body's morphological and clinical evolution during dietetic nutritional treatments. We want to be able to predict what the variables are going to be in the future. And finally, we are going to analyze the long-term adherence to treatments using home visualization technology. Okay, then this is all the information that I want to give you, and thank you very much for your attention. And if you are interested in the project and want to collaborate, we are waiting for you. I'm going to show you only an image of Alicante. It's a good, nice place to research.
All right.
Okay, thank you very much.
Thanks very much, Andreas. That was very interesting.